Okay, in this video, we're going to continue talking about probability, talk about some slightly more advanced ways of combining different probabilities to get the probabilities of more complicated events. And so, first thing that we're going to start off with is the idea of the complement of an event. So this is the event where it doesn't happen. Okay? And so, for example, if your event was rolling an even number on a die, then the complement would be not rolling an even number on a die. If your event was rolling two numbers that add up to 6 on 2 dice, then the complement would be that not happening. Okay? And so let's start with that one. So the nice thing about the complement is that it's very easy to compute if you already know the probability of the event. So the probability of the complement of an event A is just 1 minus the probability of A. And I'm just going to use this as shorthand. P of A just means the probability of A. So if you want the probability that something doesn't occur, you just subtract it from 1 or from 100%. Okay, so this should make perfect sense, right? So if it is 30% likely to rain, then it is 100% minus 30. So 1 minus 0.3, 70% not likely to rain. Okay? Or likely to not rain, I guess would be a better way to say that. Okay? So you just subtract the probability from 1. This can be really, really useful. So for example, if you wanted to do what is, if you roll 2 dice, what is the probability that they don't add up to 6? Okay? So we already know the probability that they add up to 6 is 5 over 36. So the probability that they don't add up to 6 is 1 minus 5 over 36. And you can do 36 over 36 minus 5 over 36, 31 over 36. And I haven't been doing this because I've just been leaving them as fractions, but of course you can write these as decimals. So 31 over 36 is 0.8611, or if you prefer, 86.11%. So there's an 86% chance that if you roll 2 dice that they don't add up to 6. Okay? And so you can do that in any situation, even if you don't necessarily know where the probability came from. Like the rain example, if it's 30% likely to rain, it's going to be 70% likely not to rain. Okay? You always just subtract from 1 or 100%. So that's the complement. The next thing I want to talk about is what's called independent events. So independent events are events that don't affect each other. Okay, so there's a more mathematical definition I'm not going to go into, but we're just going to think of these as things where the probability of one doesn't affect the probability of the other. Okay, so examples of independent events, just to kind of continue on the vein of what we've been talking about here. If you roll one die and another die, what you get on the first one doesn't affect what you get on the second one, right? They're unrelated. Things that aren't independent, I'll give you an example when we start talking about probabilities in tables in the next video. That's a good one, but for example, if you had, so independent, let's say that our event A is get a 1 on the first die, and B is get a 1 on the second die. Okay? So if you roll 2 dice, the number you get on each die is independent. Okay? It doesn't affect the other one. And so if we've got 2 independent events, the probability of A and B happening, so the probability of both of them happening, is going to be the probability of A multiplied by the probability of B. Okay? So in this particular case, if we wanted to know the probability of getting a 1 on the first die and getting a 1 on the second die, then the probability of both of those happening would be the probability of the first one. So what's the probability of getting a 1 on the first die? It's 1 out of 6, right? One outcome that matches our event out of 6 possible outcomes. And the probability of getting a 1 on the second die, also 1 out of 6. So the probability of getting 1 on both of them is 1 out of 36. And if you think about what we looked at in the last video, there are 36 possible outcomes. Only one of those has a 1 on both. So this checks out. Okay? So you can only do this. This only works if A and B are independent. Okay? So if the probability of one doesn't affect the other, it's the only time when you can do this. Let me give you an example where they're not independent and this doesn't work. So say you have a bag with 5 red marbles and 5 green marbles. You draw out 2 marbles. So you pull out a 1, and then without putting that one back, you pull out another. What's the probability? They are both red. Okay? So you might say, okay, I'm looking for the probability that they're both red. So we can think about this as being A is the first marble is red. B is the second marble is red. And so we're looking for the probability of A and B, the probability that both of these events occur. Right? The first marble is red and the second marble is red. And if you want to think about these, you can't think about them as being independent, because if you pull out a marble that's red, so there are 5 out of 10 marbles are red. So the probability of the first marble you pull out is red is 5 out of 10. Okay? But the probability that the second marble is red is not 5 out of 10. Okay? Because we already pulled out a red marble, so there aren't 5 red marbles left in there. Okay? And so the probability of this is not simply 5 out of 10 times 5 out of 10. It's more complicated. It's going to be something that's called a conditional probability. So when we pull out that first red marble, it changes the probability that the second marble is red. Okay? So this is an example where you can't use just probability of A times the probability of B. Okay? So we'll talk about this more later. for now, let me just write up. Probability the first marble is red is 5 out of 10. And then if you want to think about after that first marble has been pulled out, right? So we pulled out one red marble. How many red marbles are left? Well, there's 4 red marbles left in the bag out of 9 marbles total. We pulled one of the red ones out, so there are 4 red and 5 green left, and so the probability that the second marble is red is 4 out of 9. That probability has changed. And so the probability that both marbles are red is going to be 5 out of 10 times 4 out of 9. Okay? You could still multiply, but you want to change that second probability to make sure that it works. So this is, I guess, 2 out of 9. Okay? So the point here, the probability of A and B occurring is the probability of A times the probability of B if they're independent. And even if they're not independent, you might just need to think about how the first one changes the probability of the second. Okay? So if you want to know and probability of A and B, you want to think about multiplying the probability of A times the probability of B. Okay? Again, provided that you change it appropriately, knowing that A has already happened. And we'll talk more about that as we go on. Okay? Okay. Last topic in this video is on calculating the probability of an event A or B. So when you want to know what the probability is that either one thing happens or another thing. So let me give you an example of this. So let's say we roll a 6-sided die, and let's say our event A is we get an even number, and our event B is we get a number 4 or larger. Okay? So what's the probability that we get either an even number or a number 4 or larger? Well, this is easy to figure out in this example, right? Because we can just write down which numbers fit this. So which numbers fit either one of these or the other? Well, 2 does because it's even. 4 does. It fits both of them, right? It's even and it's 4 or larger. 5 fits it because it's 4 or larger. And 6 fits it, again, because it fits both of them. It's both even and it's 4 or larger. And so out of the possibilities, 1, 2, 3, 4, 5, or 6, so our probability is 4 out of 6 that we get either an even number or a number 4 or larger. Okay? So it turns out that there's actually a way to get this from the probabilities of these events themselves. Okay? So if you want to figure this out using the probabilities of the events themselves, you can use a formula called the addition rule. And what the addition rule says is that the probability of A or B is the probability of A plus the probability of B, which makes sense, right? If you want to know probability of one thing happening or the other thing happening, you should add the probabilities up, right? If there's a 20% chance of rain and a 30% chance of snow, then there's a 50% chance that you get some kind of precipitation, rain or snow, right? You can add them up. Okay? But, and the rain or snow example is a good one of kind of this example. The other thing that can happen, and the reason why that's not quite always true, is that it could do both, right? So if a meteorologist said, there's a 20% chance it will rain today, there's a 30% chance it will snow, there's probably a good overlap there that it might start raining and then change to snow or vice versa, right? And so there's not necessarily a 50% chance because some of that is taken up by the fact that it could do both, okay? And so in our formula, we take the probability of A plus the probability of B minus the probability that both happen, probability of A and B. And we can see that this is correct in this particular example. So if you look at the probability of getting an even number, well, what's the probability that you get an even number? There are 3 even numbers out of 6. Okay. What's the probability you get a number 4 or larger? Well, again, 3 possibilities, 4, 5, or 6 out of 6 total. So 3 out of 6. And then minus the probability of both happening, getting an even number and something that's 4 or larger, which means getting either 4 or 6. Those are both even. They're both greater than or equal to 4. And so minus 2 out of 6. 3 plus 3 minus 2 gives us 4 out of 6, which is the probability of A or B. Okay? And so the nice thing about this addition rule is that it can be used even if you don't necessarily know the individual outcomes and the events and things like that. So if, let's say there is a 20% chance it rains today, a 30% chance it snows, and a 15% chance it does both. Well, then the probability of rain or snow, right, the probability that you get one or the other, or possibly both, is going to be the probability you get one, 20%, plus the probability you get the snow, 30%, minus the probability of both occurring. Okay? So in this case, 35% chance of rain or snow. Okay? So the reason that this rule exists, just to talk a little bit about the theory of it, if you think about what's happening when you add together the probability of A and the probability of B, you're double counting some outcomes. So in our particular example with rolling the die, when we added together the probability of getting an even number and the probability of getting a number 4 or larger, here we counted 4 and 6 as even numbers. Here we counted them as numbers 4 or larger. And so we had counted 4 and 6 both twice. And so we had to subtract that off, those counts, to get the actual values. Okay? So the last thing I want to talk about in this video is looking at probability from a table of values. So let me give you a table of values. Let me go ahead and write this up. So this is research. This is from the Pew Research Institute. It's about the political parties of people in the United States, their political affiliations, based on their race. Okay, so if you don't already know this, the race of someone changes the doesn't change the political party that they necessarily support. What is true is that people of different races are more likely to support different political parties. So we're going to split this up. This is actual data from 2016 on whites, Hispanics, and blacks, and which political party they support. So I set this up by taking 1,000 people total. So if you took 1,000 Americans, 653, 1,000 white, black, and Hispanic Americans. Of course, there are people who aren't any of these three races. But if you took people who identify as white, Hispanic, and black, if you took 1,000, 653 would be white, 152 would be Hispanic, 195 would be, 195 would be Hispanic, and 152 be black. And then if you look at their political affiliations, 353 of the whites would be Republican, 46 would be independent, 254 would be Democrats, 53 of the Hispanics would be Republicans, 20 independent, and 122 Democrats, 10 black Republicans, 9 black independents, and 133 black Democrats. Total of 416 Republicans, 75 independents, and 509 Democrats. Okay, so this is again 2016 data. So this is a table of values. You can read probabilities off of something like this. So for example, if somebody asked you, what is the probability an American is a Republican, that probability would be there are 416 Republicans here out of 1,000 total. So you would take 416 of the outcomes match your event out of 1,000 total. So 0.416 or 41.6% of Americans identify as Republican. Okay? So in our next video, we'll talk about conditional probability and digging deeper into these kinds of tables and reading off values.